Hello everybody, this is Dr. Eugenia Celurrio and we are going into lecture 6 of the Module 1 Introductions to Complex Finite Dimensional Hilbert Space. In this lecture, we're going to talk about orthogonality and orthonormality, and then we are going to talk about what is the basis of a Hilbert space. Before we delve into anything else, I'm just going to make a recap of the things that we've seen in previous lectures that I'm going to be using in this one. First one is the closure of a set or a subset. So remember, we are on a norm space, and the closure of a subset of a norm space is just adding all of the points that the Cauchy sequence of this set should converge to. In the case that this is the whole space, the whole norm space, well, we just add those points. The linear span of a set is just the finite linear combinations of the elements of this set. And from now on, this H will always denote a Hilbert space, and just as a small reminder, a Hilbert space is a vector space for us over the complex numbers. It has an inner product. It is also a norm space when we define a norm using this inner product. The norm of a vector is just the inner product of the vector by itself, and then we take the square root. And it is a Banach space, meaning it is complete. If you don't remember any of the full definition of these concepts, we have 5 lectures explaining them in detail. These are the main things that we are going to need for this lecture. So let's go into this. We have an inner product space. Bear in mind that right now I'm not saying that this is a Hilbert space. In order to define orthogonality, we just need to have an inner product. So we say that two vectors, x and y, are orthogonal whenever we do the inner product of x and y and we obtain 0. We write this x is orthogonal to y. We say that they are orthonormal if they are orthogonal, and we also have that the norm is equal to 1. Again, remember that as soon as we have an inner product, we have a norm defined by this inner product, and this is the norm we are taking here. So we have that two vectors are orthonormal if they are orthogonal and the norm is 1. So let's take an example. For example, Cn with the usual inner product that we have already used. And we take two vectors, the vectors 1, I, 0, and the rest of the coordinates I0, and the vector y, which is I, 1, and all the rest of the coordinates are 0 from the third onwards. When we make the inner product of these two vectors, so the first coordinate of x is 1, the first coordinate of I is minus I, because, well, the first coordinate is I, and we are taking the complex conjugate, so minus I. And then the second coordinate is I, and the second coordinate of I is 1, so the complex conjugate of 1 is 1 still. So we obtain I minus I, and that is 0. So these two vectors are orthogonal. However, they are not orthonormal, since the norm is for both of them is 2. So checking that two vectors are orthogonal is as easy as making the inner product, and as long as we have the inner product specified, that should be easy enough. Now let's see some remarks about this concept that we just saw. The first one is that the 0 vector is always orthogonal to every other vector. So then, considering the 0 vector when we are talking about orthogonality, it doesn't really bring us anything. Now, just a small teeny tiny remark, the 0 vector is not orthonormal to any vector, because the norm of the 0 vector can never be 1, it's always 0. Now, A very important detail is that if we have two vectors that are non-zero and they are orthogonal, then they are also linearly independent. Let's prove that. In order to prove it, we are going to use the proof by contraposition. So we are going to take x, y, two vectors that are not zero and they are linearly dependent. Well, if they're linearly dependent, we have alpha, a complex number, such that we can write one of them as alpha times the other. In this case, I chose to write x equals alpha y. Since they are different from zero, this alpha must be different from zero too. Then if we take the inner product, well, we substitute, we just saw that x, because they're linearly independent, is actually alpha y. And using the linearity of the inner product, we obtain alpha inner product y and y. And this must be different from zero. Since y is different from zero, the norm of y cannot be zero. And since neither of them are zero, alpha, where x is not zero, alpha cannot be zero. So then this product cannot be null. So they cannot be orthogonal.